This video is on compound transistors, or sometimes also called composite transistors. So a compound transistor or composite transistor has a few things that are kind of characteristic of them, and they are compound or composite transistor. It still has the same number of terminals as a single transistor. So for a BJT, you know a BJT has a collector, a base, and an emitter. That's not supposed to be a ground right there. Shouldn't be a line there. And a MOSFET has a drain, a source, and a gate. So a composite BJT-based transistor, composite transistor. So a BJT-based composite transistor still has to have three terminals, has to have a collector, a base, and an emitter. And a composite MOSFET-based compound or composite transistor has to have a drain, source, and gate. And they have to kind of have the same function. For example, if you increase VBE, your current increases. That still is true for all of the composite or compound transistors that I know. And same thing over here. You increase VGS, and the current, the drain current increases. So you still have those same three terminals. That's important. But it's not just a single transistor anymore. It's an entire circuit, but that circuit has three terminals, and it's more complex. And the reason for making it more complex is to improve something about a transistor. So for a BJT, you increase VBE, the current changes exponentially. But if you could get it to the third now, or not the third, but I don't know, exponentially squared or something, then that would be, now when you throw that current across a resistor, you're going to get a bigger gain. Same thing over here, or maybe your Rin, maybe you want to use this as on the input stage, but your Rin is just R pi here. So a compound or composite transistor would maybe give you a higher Rin. Okay, so let's look at our first compound transistor. And those are cascoded transistors. So a cascoded transistor has two transistors of the same type. So if it's an NMOS, it'll be two NMOS on top of each other. Once you do the small signal analysis, you'll see why, but this is always biased. It's some DC voltage on here. You can use this in an amplifier, so this will either be V in or a V bias, depending on how you're using it. So a cascoded transistor, once we see the superpower, we'll come back and look at when you use V in and when you use another bias. So this would be V bias 1 and this would be V bias 2. Or if you were using this flipped, then you'd have the supply and then you'd have two PNPs. And this would be VB1 or V in. And this would always be a V bias. It's never going to be a moving signal. Or if you have BJTs, and you'd have two NPNs, and same thing, either V in or VB2, one of the two. It's either DC or it's your input. This one is always a bias voltage. Or if you have PNPs, then again, have two PNPs. And this is V bias 2, and this is either V in or VB1. Okay, so we mentioned that compound transistors always have the same number of terminals as a usual transistor. So the transistors we're looking at right now are BJTs. So you need to have a collector, a base, and an emitter. So let's just look at this one as the example. What you see here is, this is where the current comes out. So this is the collector. This is internally biased, so this doesn't come out. This isn't considered a terminal. This is your emitter, and then this becomes your base. Whoops, that's not BJTs. So this would be your collector, your emitter, and your base, and this with the internal circuitry or whatever, this is not considered a terminal. So you've got your collector, your base, and your emitter. And you can see this is a 3-terminal. It can be treated as a 3-terminal device. Okay, so that's one condition of being a compound or composite transistor. And it's not a single transistor anymore, so that's a second part of what you see in compound or composite transistors. And then the third thing is that it has a superpower over a single transistor. So you possibly have already seen this in class, but if you, I'll post a handout with all this kind of summarized on it, but let's see if this will all fit. Let's see. Not fitting very well, but well, too late now. So what you see with the, that's weird. Up here, let's add cascoded JT. For a cascoded BJT, if you look at the base emitter, the base emitter is just across a single transistor. And so the base emitter resistance is still R-pi, just like a single transistor. So nothing changed there. If you look at its R out, in other words, the perceived resistance at the collector, you actually see a really big value. So the R out is very different than a single transistor. Single transistors, its R out, in other words, its collector resistance is just RO, but for a cascoded transistor, you get GM2, so this would be Q2, to Q1. You'd get GM2, so that transconductance of the top transistor times R-pi, and I forget which ones these are. I'll check those out before I post. But yeah, times R-pi times RO. And if these are the same transistors, then these values won't vary very much. They should be the same for both transistors, I think. R-pi is beta VT over IC. IC is the same, so that should be a constant. And then RO is VA over IC. So yeah, they shouldn't change whether it's Q1 or Q2. Okay. And then the GM, this is a single transistor. Your GM is when V in goes up, your current into the transistor, into the collector goes up. So it's actually considered a negative GM, but it's the GM of Q1. Your VBE on, your VBE just has to get to VBE for the device to turn on. It's the same VB on as your single transistor. For the VCE SAT, both of these have to be in the forward active region. So for Q1 to be in the forward active region, this node needs to be VCE SAT. And then you need for Q2 to be in the forward active region, it also needs a VCE SAT across it. So, and it's starting at VCE SAT. So it goes another VCE SAT. So the VCE SAT for a cascoded transistor is actually double what it is for a single transistor. And its superpower is the higher R out. And I won't go into it here, but when you're trying to make a current source, sometimes you say, oh, a current source has a high R out. The higher the R out, the perceived resistance at the collector, that means that when you change the voltage at the collector, if it's a really high R out, then changing the voltage at the collector doesn't change the current. And that's what a good current source is. If you change the collector voltage and the current doesn't change, that's a great current source. And again, a high R out just means exactly that. When you change the voltage at the collector, if the current doesn't change, hey, that's a high R out and a great current source. And also, if you remember with a common emitter, as you increased the resistor value, so the passive load, your gain increased. So you'd like to increase that resistance or that perceived resistance of the resistor up top if you're doing an NPN-based common emitter. That resistor up top, you'd like to make that look really big. And turns out that by replacing that resistor with a PNP-based or a PMOS-based cascoded transistor, you get massive gains. You get gains in the millions. So is having this high R out is great if you're making a current source or an active load for your amplifier. And the drawback, I'll add that to the handout too. But the drawback here, if you notice, you need a bigger voltage across your quote unquote transistor, your compound transistor. So your supply voltage sometimes has to be higher. So that's a cost. And for the MOSFET, your Rn is infinite, which is the same as for single transistor. The R out equation is a little bit different. For BJTs, it comes out to R pi, but for MOSFETs, it comes out to RO of the two transistors. So if you call this M1 and M2, it's the RO of the two transistors multiplied. You'd think that because they're in series that you would add them, but if you do the small signal analysis, you'll see that R out is approximately GM times RO times RO1 times RO2. The GM is the same, VTs are the same, and it has the same problem that you need two VDSAT because you have two transistors and you want them both to be in the forward active region. You need two VDSAT, so one VDSAT here to keep M1 happy, and now because the source is at VCSAT and you need another VCSAT across M2 to keep M2 happy, then you end up with two VDSAT minimum at the drain. So it has the same drawbacks. You sometimes have to use a higher supply because now you have to have two VDSAT across it instead of one VDSAT. And the other thing is because of its high R out, great for current sources. Again, a high R out just means if you change the voltage, the current won't change very much. And then also as an active load. Whereas before we used a single transistor as an active load, you can use a PNP-based or a PMOS-based cascoded transistor and replace your active load with a cascoded load, and that'll give you like 10,000 times more gain, 10,000 times larger gain. Okay, and I'm going to continue on. There's multiple compound transistors that I want to introduce, but I just this one spend a little more time on, and we'll continue on in the next video.